How is everyone? Sleepy? No? All right. So let's start. Any questions from previous session? Okay. So in the last session, we talked about general machine learning framework, right? Do you recall 5 components? Okay, now we will take one concrete algorithm. Okay, your first machine learning model called logistic regression. Okay, before that, we'll talk a bit about different machine learning problems. Okay, so this is your machine learning algorithm. So there are 3 types of algorithms. One is called supervised algorithms. Unsupervised algorithms and reinforcement learning. Okay, there is something called as semi-supervised algorithm between these two. I'm not adding all of them. Now, how do this classification works? So in this case, we said that in training data there are 2 components, right? Data X and label Y. Correct? Whenever this label is present, it's a supervised algorithm. So we are giving examples and we are also giving labels. In unsupervised, we only have examples without any labels. Okay, RL will not talk about it. Okay, in this session. So this is the difference between supervised and unsupervised. Okay, within supervised, we have 2 types. One is called regression, and second is classification. And in unsupervised, you will learn what is called as clustering. There is a session on clustering, I think, day after tomorrow. That is over here in unsupervised. Okay, we will not talk much about it. So regression will be covered tomorrow. Okay, regression, what happens is that this Y or the label is a real number. Label is a real number. And here the label is an element from a discrete set, certain discrete set, like 0, 1, right? -1, +1, red, blue, green. Got it? So that's classification. So classification, there are 2 classes. Again, there is a binary classification and there is a multi-class classification. In binary, there are only 2 classes. In multi-class, there are more than 2 classes. Clear? I'll stop here with the taxonomy. There is one more class which is called as multi-label. So multi-label is common across everything. So in regression, if you just have one label to predict, it's a single label problem. But instead of one label, sometimes you might have to predict more than 1 labels. Then it becomes multi-label problem. Multi-label regression problem, multi-label classification problem. So for example, you are given an image which has got multiple fruits. So image has got multiple labels. Let's say there's a fruit platter containing mangoes, banana and orange. Then image will have 3 labels: mangoes, banana and orange. It's a multi-label problem. Got it? And what is multi-class? Multi-class, we just have one label from a set which contains more than 1 label. By the way, there could be also multi-label, multi-class. That is also possible. Okay, but don't worry about that right now. Just be aware of that. Questions? Do you want examples of this? Regression. Can you give me a regression example of regression problem? Yes. Stock price prediction problem. Yes, for sure. Yes. Huh? Housing price prediction problem. Good. Or how much? What will be your performance in quizzes? Whether you will get a certificate or not. What is that problem? Binary classification problem, right? You get a certificate or not. There are so many factors, correct? Whether you attend, whether you participate, so many factors, right? If you are processing loan application, for example, you get a loan or not. What is the type of problem? Binary classification problem, right? So let's say there is a problem where you have to recognize fruits out of 10 different fruits. What is the problem? Multi-class classification problem. Good. Yeah, so you are sorted. Everybody with me on this? Fairly straightforward. Remember this taxonomy. This big picture will be very useful throughout the course. Okay. And then there is a multi-label twist. Each of them can have multi-label versions. So stock problem, stock prediction, right? If you want to make prediction for next 7 days, you need to predict multiple values, right? So it becomes multi-label regression problem. Getting it? So if there is a binary classification problem, but let's say an image may have both the things. So it could be multi-label, binary multi-label problem, or multi-label problem, or multi-label multi-class problem. Huh? Clear? Any questions? No questions? This is the most important thing. Now, logistic regression. This is interesting. So this makes it a bit confusing. Regression, the term regression, right? But logistic regression is a classification problem. Logistic regression is a classification model. Got it? Tomorrow you will be learning linear regression, which is a regression problem. Today we are going to focus on classification problem. Getting it? Okay. So let me write. Logistic regression is a classification model. Okay, now question answer session. Now you know that this is machine learning model. Now ask 5 questions and get all the answers, right? Okay, so what is the first question? Training data. Now we have a tool set. Okay, so how does training data look like in logistic regression? We have every example, right? We have examples. So let's say we write examples like this: x1, x2, xn, n examples. Got it? N examples. And each example will have m features. Got it? Remember, this is also x, but it is subscript. This x1 is first feature, x2 is second feature, xm is m feature. These are features. Got it? Understand this carefully, huh? So you have a matrix like this, which is n cross m matrix. So this is basically, this is called as feature matrix, and it is denoted by capital X, and this is typically boldface matrix. Got it? And this matrix has got n examples. Each example is, what is each example? Each example is a vector. Each example is vector with m components. Typically, there is a convention that we represent vector. This is a vector, right? X1 is a vector. The first example. Vector is always a column vector. So this is x1 1, x2 1. Getting it? There are getting complicated, right? There are m features. Okay, this one is index of exam, and this one is index of feature. Getting it? If you are trying to solve, let's say, housing price prediction problem, and let's say we have two features, one is number of bedroom and second is area in square feet. Got it? So this is number of bedrooms and this is area in square feet. Got it? So every example will be a vector with two components. Got it? So now if you come back to this matrix, right, we have represented this vector as a row vector. So this is essentially, we have this vector 1 is transpose, right? So this feature matrix has got individual example vectors which are transposed. So they are represented as a row vector. Huh? Listen carefully. If you have questions, we will go through it. There is no hurry. Getting this understanding well is very important. Huh? Clear so far? So good? Is clear, right? Now let us look at the another component, which is a label. Since you are solving, let's say, a binary classification problem or even multi-class case, we have a label vector. But let's first talk about binary. It is typically denoted by small face, bold face, Y. Small case, bold face. Small case, bold face meaning a vector. Small case, bold face. Small case, bold face is vector. Huh? And uppercase, bold face is matrix. Now this will have again y1, y2, yn. Right? Each example has a single label. Right? Binary classification problem we are solving. Each example has a single label. So we get y1 to yn. This is label of example 1, label of example 2, label of example 1. Clear? Clear? We are just doing slowly. Huh? So how does training data look like? Let's write it down. So D, capital D is a training data. So each example is a vector. X, xi, comma yi. I goes from 1 to n. Xi, this is vector, this is also vector. Again, I will make bold face. Bold face, small case, vector. Clear? This is the training data for your binary logistic regression problem. Okay. So now in case of, now you will have to tell me, we are solving the digit problem, right? Digit classification problem. Handwritten digit classification to be specific. How does the data look like? Tell me what is xi mean? What is xi and what is yi? Right, now this is basically what is the type of this classification problem, first of all? Multi-class problem. Single label multi-class problem. This is a multi-class classification problem. Good. Multi-class classification. Okay, so how will this look like? What is X? X is black and white image. Let me draw this black and white this time. Right? 28 cross 28. You can flatten this and open this up as a vector. X1, X2, all the way up to X 784I. Remember, these are not boldface. These are not boldface because they are single number, right? They are not boldface. So Xi, this is the index. This is the label. Sorry, this is the feature. X1, X2, X784. Clear? This is how each example will be given. And how will be yi? Yi will belong to one of these. 0 to 9. No? Let us solve a very simple binary classification problem here, where we say that I want to detect digit number 5, whether digit is 5 or not 5. So digit 5 becomes binary classification problem, where we have label 1 and label 0. Label 1 if it is digit 5, label 0 if it is any other digit. That's, we will first solve this problem, later we will come to this. This will need some more setup. We are not yet ready for that. Clear? Binary setup is clear to everyone? No issues here, correct? Let's move on. Okay, so here the data is, how does data look like? Again, vector, scalar, 1 to n. N examples. Every example is represented in 784 dimensional space. This is binary. This is either 0 or 1. Slightly more formal way of writing. Got it? Okay, let's move on. Yeah. How many instances of which each digit? Yeah, so roughly, let's say there will be equal number of examples. Yeah. So we will be later using MNIST data set for our practical purposes. In MNIST, this MNIST digit data set, handwritten digit data set, it has got 60,000. Generally, people use 60,000 training examples from this. All right. The training data is gone. What is the second part? Model. Good. Okay, interesting. Now, what do we want? We want to predict whether the label is 0 or 1. So we want binary output 0 or 1. Correct? So here what we do is we'll have a model that is something like this, which has got two stages. So we give this x as an input. This x is a vector. This ith example. This goes as an input. And there are two blocks. And you have an output, which is y, I. So in goes features. Now there are two blocks inside. This block is basically a linear combination block or linear function block. And this block is nonlinear activation point. Just write it, I'll explain each of these things. Okay. So what will happen is, let's look at the first block. Okay. So we are sending this xi, correct? And we are going to take a model which is hyperplane. Okay. Or a line, linear model. Think of it as a linear model. If you have just two features, one feature we have a line. If you have three features, we have a plane. If you have more than three features, we have hyperplane. So we have 784 features here. So we have hyperplane. So what we do is, let me write this. So we get z. This z is equal to b plus w1 x1 plus w2 x2 all the way up to w784 x784. So generally you will write this like this: b plus w1 x1 plus w2 x2 all the way up to wm xm. M is number of features. Right? How many unknowns are there? How many unknowns? M plus 1 generally. Here 784 plus 1, which is 785. Clear? Okay.
Yes, sir. Yes, yeah.
Clear, no? Okay. So these many unknowns. So these are all unknowns. So what would this produce? What kind of quantity will it produce? Let me take an example. A small example, right? So let's say we have a vector xi with two features, 1, 2, correct? We have a w. W is again a vector, value 0.1 and 0.2, and b is 0.5. What would be the value of z? Z is equal to b plus w1 x1 W2 X2. Calculate the value, do quick calculation.
It is 1.
How much?
It's 1 actually.
1. Get it? So we are getting a real number as an output. Fortunately, we got 1 here. That was not intended. Right? We got 1 here, right? But let's say I change it to, let's say, 10 and 20. What happens? What do you get?
50.5.
Huh?
50.5.
50.5. So point is that this Z is a real number, correct? And we want a value which is either 0 or 1. Are you getting the point?
Yes. Yeah.
So we need to do something, right? So we need to take this real value, pass it through some other function that will return us value
0 or
either
1.
0 or 1 or between 0 to 1. Huh? So what is that function? So in case of logistic regression, we have a function called a sigmoid function. By the way, we use sigmoid function in logistic regression. So what is the idea? Idea is that take any real value and return a value between 0 and 1. So this function looks something like this. This is your input Z, and this is your sigmoid of Z. Okay. So this sigmoid function returns value between 0 and 1. 0 and 1. So this function passes getting it? So this function takes a value between 0 and 1. As you get a strong positive value, you get output as 1. Okay, so let me write this. So sigmoid of 0 is 0.5. Okay. Sigmoid of something like 10 is approximately equal to 1. And sigmoid of minus 10 is approximately equal to 0. Huh? You have not yet talked about the way this looks like. So this is sigmoid of Z is 1 upon 1 plus exponential of minus Z. That's a function. Okay. That's the mathematical form of this function. But you get the intuition, right? Intuition is that you have a real number, we want to convert that into something between 0 and 1. So we use this function. All right. Any questions so far? We'll complete the picture. Yes. Uh-huh. So what scalability? Are you talking about scale of features? Uh-huh. Yeah. So if it is in tens of thousands, right? Once it goes beyond certain positive value, it will be very close to 1. Doesn't matter. So if you are talking about scalability in terms of, so there is one requirement, of course, each feature has to be on the same scale. Each feature, this is mandatory in sigmoid function, in logistic regression. Each feature has to be on the same scale. So we need to normalize data before using this particular method. We need to normalize the data and bring it on the same scale. That is one important aspect of this. Okay, so is this clear, sigmoid function? So how is it looking now? Now let's complete the story. So logistic regression, we have Z, which is B plus W1 X1 all the way up to WM XM. So I'll also write this in a compact form. Wj Xj, G goes from 1 to M. Right? So sometimes what people do is, in order to make it very simple, so they also, for B, they call this as W0 plus W1 X1 plus WM XM. And they introduce a dummy variable X0 and set this to 1. Set it to 1 always. So you get basically a very compact representation. J goes from 0 to M, Wj Xj. And now you will realize how the vector matrix multiplication comes into picture here, right? So basically we have, so this is nothing but W0 X0 plus W1 X1 all the way up to WM XM, correct? So now Z is equal to W0 X0, W1 X1, WM XM. So now you can represent this like this. Correct. This is a weight vector and this is your column vector. This is your feature vector. So we'll see some such kind of thing. I'm just showing this only one thing to you and then I'll move on. I'll not write this complicated maths. You will get all, yeah, you might find this a bit boring or a bit difficult. So we write this as, this is now become vector, right? This W transpose X. So this is for ith example. So Zi becomes this. Right? So if you actually know Python a bit, you know that you must be knowing that such kind of vector matrix multiplication is way faster than doing it this way. And if you represent all your machine learning operations in this particular form, coding it in Python, every function literally is one line code, literally one line code. We'll show that in practical. No? Yes, we will show that in practical. That every single thing is like a one-line function. Every function has a one-line code, which is in this matrix vector format. And this is exactly where linear algebra enters. Understood? No? So you can actually do this multiplication and verify that this is really this. Do you see that? Or should I do it? Should I do it? See, it goes like this, right?
Yeah, no, sir. Yeah, clear.
this is equal to this. Verify that. Clear?
Yes, sir.
Okay, good. Any questions? So whenever you see some such kind of cryptic equation, work it out. Take a blank paper and write it. Awesome. We can go forward and we can actually do this computation of Z for all example at once. That can also be done using this. You want to try that? I'll just show that for fun. So you can calculate Z, the vector, which has this element, right? Which has got Z1, Z2, Zn. We are calculating this Z for every example, correct? So you can do this like this. You can have X, which is matrix X, which is a feature matrix, times W vector. We'll verify very quickly. We do it with, let's say, two examples. So let's say this your first example. Let's say there are only two features. This is your second example. This is your third example. Getting it? This is your feature 1. This is feature 2. Huh? Getting it, no? And this is dummy column that we add with 1 everywhere. And now we have W vector. We have this W vector. And W vector will have how many entries? How many entries will be there in W vector? Yes. 3. Right? There
It will be
is
3. Yeah.
W0, W1, and W2. Are these matrix compatible? What is the size? This is 3 cross 3. This is
3 into 1.
3 cross 1. What will be the output? 3 cross
3
1.
cross 1. 1.
So check out what will be the output. Let us write it down. Goes this way, comes down this way. Simple 12th class matrix multiplication. 12th class, no? Or you studied in 10th class? I don't know. Right? You write this. This is W0 plus X11 W1 plus X21 W2. Correct? This is for first example. Second example, third example. Fill this up. Clear? With just this single equation, you're knocking it off. All Z's are calculated. So to some extent, machine learning is nothing but matrix multiplication, set of matrix multiplication, vector matrix multiplication. This view will be extremely useful when you go to deep learning. Got it? Any questions? No questions? Good. This is clear, right? How this vector matrix is coming into picture? All right. So now let us complete the story. The story is, so the model, 2 steps. Z is, so Zi is W transpose Xi, correct? And Yi is sigmoid of Zi. we can simply write this as sigmoid of W transpose XI. This comes from here.
From Zoom.
Yeah.
So person is asking like, why can't we simply look at the maximum value and minimum value of Z and we convert it between 0 to 1?
Maybe he's discovering another algorithm. Yeah, that's not how linear regression works. Logistic regression. Logistic regression uses sigmoid function. But this diagram gives you freedom to discover new algorithm. You can try your own stuff, own nonlinear activation here, and you will have your own algorithm.
No, that I understand, sir. But what is a compelling reason or underlying assumption about the data distribution that logistic distribution uses?
Okay, underlying. So, what distribution are you talking about, sir?
No, I'm talking about logistic regression, right? It converts a number, a scalar, to 0 and 1. So
Right.
it must be using, see, it's not a uniform distribution. It doesn't assume all the numbers are uniformly distributed. Just to quote an example.
Yeah.
So what is a compelling reason to use this logistic sigmoid function?
So the question, so the idea is like this. Maybe I will try explaining in a slightly different way. So typically, see, this is what we are interested in. So let's say we have data like this. Let's say there are these two classes. And let's say we learn this classification boundary. So what we want is around classification boundary, we are not so certain about what class it is, right? So there is a lot of confusion around classification boundary. But as we move deeper into this part or deeper into this part, we become more certain about labels. So we want a function which is mimicking these characteristics, for example, right?
Okay.
So so imagine, so you know, so there is this very, very dark black color in this side, very dark red color in this side, but the color over here is a combination of dark black and red. So you are not so sure in this region. This region is not so sure. Here you are totally sure. Here you are totally sure. So that is basically given by this sigmoid function.
Which no other function has. That's what you are saying. Which is one of the unique feature of this. Okay.
Yeah. So basically, the probability is very high. From high it goes to low to up to 0.5, and then again from 0.5 it again goes up to 1. So there is some such kind of thing happening in the in this space.
All right. Thank you, sir. Yeah.
Yeah, this is another view I really like about why sigmoid function, because around this boundary, right? Around this boundary, there is a lot of uncertainty. We are not so sure, but as we go away from boundary, we are more and more sure about what class we are predicting. Okay, thanks for asking that question. So this is the story of logistic regression. Took us a long time to arrive at this. Clear? Two-step process. And what are the parameters? Parameters are, what are the parameters here, by the way? And this is an important question to ask. Some people get lost in this. What are the parameters here? Only WT. Sigmoid function itself does not have any parameter. Only parameter is this WT, which comes in linear combination. Huh? Clear? So sometimes you might also see people writing like this: B plus W transpose XI, something like that. You might also see some such kind of thing also. But let's stick with this. Okay, clear? All right. So keep this in mind, okay? This is, and by the way, logistic regression is one of the important building block, foundational building block in neural networks or deep learning models. So whatever we are learning here will get replicated in neural networks. Okay, but this is important. Got it? So in neural network, every neuron is a logistic unit, logistic regression model. Every single neuron is a logistic regression model. It has got such kind of 2 blocks. All right. Any other questions? What's the next step? What is the next component? Yes? Answer that. Are people sleepy? Say loudly, loss. Let's say loss to make profit.
Loss, yeah.
So how does loss look like here? Let's try to work it out. So what is the loss? What is the notion of loss? Let's first write that. So we have 2 possibilities, correct? So yi is either 0 or 1. Actually, we might predict 0 and 1, 0 or 1, right? So when actual label is 0 and predicted label is 0, what loss will you assign? Good. People are awake. If you have 1 actual, you predict 1, what is the loss?
1.
1? 0. Good. Okay. Now these are 2 issues, right? We have to figure out what loss to give here and in this case. Correct? So let's draw something. So there is label 0 and label 1. So when label is 0 and I predict 1, I basically want to give a very high loss. And when I come to 0, the loss should go down like this. Yeah, my drawing is not that great. I'll write the function name of this. Okay. And when the other way around this goes, so I want to basically, when it is 0 but it predicts 1, put a loss like this. Okay. So what is a net function? If you add these 2 things up, right? How the net function will look like? I'm again trying, may not be.
It will be again U-shaped. Yeah.
What is this function? Is it convex? Convex function, single minima. Right? Convex function. We are lucky. Whenever you have convex function, we are lucky. We know how to solve it. So this is called as binary cross entropy loss. Very big name and scary name, but it is what it is. Getting it? Let's write it mathematically. I don't want to make mistakes, so I'll open my notebook. Loss. So this BCE loss looks like this. So let's again follow the convention. G of W, which is BCE this time, is BCE, by the way, binary cross entropy loss, BCE loss. So we again normalize for examples one by one. By the way, remember this minus sign, negative sign. We sum over 1 to n example. We have to find out loss per example, correct? So that's why there is sum over 1 to n. So the loss is, we have yi, which is the actual label. Okay. Log of yi, but I'm putting a hat over here. Is prediction. Plus one minus yi log of 1 minus yi hat. Okay, we'll work this out slowly. We'll see what it means. Huh? Okay. All right, how do I get rid of that? Idea. Do you know how to do it? I think so. That's it. Erase. Okay, good. Yeah, I'll do that. Thank you. It requires 2 engineers to operate this. Sorry, again, complicated equation. We'll work it out. Have patience. Let's take a case when let's say yi is equal to 1 and y hat I is equal to 1. Let's work out what is the loss. So you have this equation, right? Yi into plus 1 minus yi log of 1 minus. I'm just focusing on this part, okay? Ideally, this is called entropy. So this should be minus. This minus, I'm getting it inside. This minus, I'm pushing inside. There is entropy. So what will this result into? Yi is 1 log 1 minus 1 minus 1 log of 1 minus 1. This will result into 0 error. Correct? Everyone is clear about this? Now take other case where the misclassification, we have 0 here. Okay, good. Yeah, I should explain that. Thanks for asking. So y hat is basically the predicted label. And yi is Thanks for asking. Yeah, sure. Yeah, you can have value in between that. I'm just using this for simplicity. just for simplicity. But the value that you will get will be between 0 and 1. It could be any value. Yes. I'm leaving that for Professor Nipun to talk about it tomorrow. This actually comes from what is called as Bernoulli probability distribution. Okay, but I am not introducing that explicitly because I will lose a lot of you, or some of you at least. I don't want to do that, so we are taking it step by step. So there is a plan to introduce Bernoulli distribution tomorrow, and then you will again come to this. So this BCE will be derived from Bernoulli distribution. Bernoulli distribution is basically coin toss. You toss a coin, you get 1 or 0, right? It's a Bernoulli distribution. Same thing is happening here. You are getting either 0 or 1. So leaving something for tomorrow. Okay. You had some question, or if sure. Sure. This one? Oh, you are right. You're right. This should be y hat. This is a prediction. So this is y. Thanks. This is useful. Let me go back and correct it everywhere. No, that was this. So, y hat. Yeah, thanks. So as a convention in machine learning, we generally put hat for prediction. Okay, whenever you see hat, it means it's a prediction. Cool. So this function, right? Nipun, correct me if I'm wrong. This function over, sorry. This function over here is actually minus log x. Log reflection of the log function, basically. And this is basically the other side, which is this side, is minus log of 1 minus x. You can plot this function separately. In just a minute. In Matplotlib, you can plot it in Python and just verify. Okay, so whenever the label is 1, but we are predicting 0, we assign penalty according to minus log of 1 minus x. And there's a small component coming from this, around this part. And opposite for them. Clear? This is slightly more mathematical than morning. So please ask questions if you have any. Yes, you had a question. This one? Yeah. We can also do that. You can also y hat equal to 0. I just want to see what comes out of this. So see, now let's work it out. No. So yi is 1. So you have 1 log of 0. And this term is 1 minus 1. So this will be 0 basically. So what is the loss here? Log 0 is? Log 0 is 1, right? Log 0 is, sorry, log 0 is infinite. So this is infinite. Loss. Which is what should happen here, right? At 1, we are putting infinite loss.
Yeah, it's a huge loss.
And at 1, we are also putting, so you can try other way around also. So where you put yi is 0 and y hat of I is 1. Check it out. Check this out. Check out if you're getting infinite loss in this case also. Any questions so far? Otherwise, don't get disheartened if you're not able to follow maths. It's okay. Because that's how we have designed it. We want to say that if the label is 1, if you're predicting 0, you want to put infinite loss. This is how we have. Again, I told you, right? Loss function does not come automatically. It is something that we specify. Okay. So do you want something like this? But what will happen is that, see, you will put far more loss around this region, right? If I'm predicting, see, where is that? So basically, if you do that way, right, you will also assign loss in this region, which is quite substantial. Right? In this region, loss is substantial, where you should not be giving so much of loss here, correct? Because you're going well inside you're going well inside here. You're going well inside this region, and still you're assigning significant loss, which is not which is counterintuitive. Or if you go here, you're assigning significant loss. So that is, we don't want that type of thing. Are you getting what I'm saying? Is everyone getting? This is a very nice question actually. That why this loss makes sense? Why such a aggressive loss makes sense? Because see, as we go inside this region, right? If we go here, you don't really want to assign a loss if you are correctly classifying. Why do you want to assign loss? There is no loss, correct? So as you go deep inside this, you want the loss to gradually go down to 0. And as you go here, you want loss to be. So the idea is that if the point is from this region and you're assigning it over here, loss should be infinite. So you're doing far greater misclassification. Point is from here, but you're putting 1 plus 1. Plus 1 is really, it's really for the points which is deep inside. So BC is the general loss people use for binary classification. Even in neural networks, you will see binary cross entropy loss for binary classification. This is how people do it. And that's the reason, that's what I'm explaining, the logic of this. Whenever you're assigning probability of 1, you're basically totally doing your boundary is not at all, this classification boundary is not correctly set. Are you getting the intuition? Are you getting the intuition? Okay, if you have questions, ask, okay? Here, right, around boundary, it should be 0. This is probably, I have messed it up completely. Let me have a fresh picture. Let's say there are these points, right? It's the classification boundary. So if point is here, if there is a blue point here, there is no penalty. When blue point is here, y hat would be 1 for this point. If there is a black point here, y hat for this point will be y hat equal to, this will be 0 basically. Right? Ideally it should be written like this. So this particular model predicts this probability of y equal to 1 given x. Right? So which is 0, y is equal to 0 in this case. Right? There is. So if you use any other loss, it will not work this way. So if the point is from this area and you are assigning this class, there should be infinite penalty. If point is from this area, you are assigning to this infinite penalty. If point is somewhere around here, you are much lenient in penalty. You don't want to give too much of penalty because this is any area of uncertainty. You're not sure it could be this way or that way. So you're far more lenient in this space, but in the extreme, you're very aggressive. That's why this loss makes sense. I also discovered something. I never thought deeply about this. This is the beauty of teaching. And thanks for questions. Got it? Huh? Good. So that's why these kind of losses don't make much sense. Because this will unnecessarily put loss even when you're correct. Even when you're in a correct region, this will put losses. You should not be putting anything. All right. Anyway, if you are confused with all this discussion, remember that this is the loss function. Huh? And this looks like this, which is convex. It's good enough. Other things are quite deep discussion, whatever we had. All right, what is the next part? What is the fourth component? Yes. Optimization procedure. So we'll write the loss first. The loss is J of W 1 by N. I is equal to 1 to N. Yi into log of y hat I plus 1 minus yi into log of 1 minus y. The loss function. Correct. Now we will do it slowly, gradient descent, right? You want to now we are going to use gradient descent procedure. Let's write gradient descent procedure. I will come back to this slide in a minute, but let's go and open a new slide. Four-step procedure. First step is randomly initialize now this is lowercase boldface. What is it? Vector, weight vector, correct? And weight vector will have components. How many components will have weight vector will have? Yes. If there are m features, how many components will be there? M plus 1. Good. So there will be W0, W1, all the way up to Wn plus 1. Just use this small face. W0, W1, all the way up to Wn plus 1. You will randomly initialize them. Okay, put any random values. Now, second step is repeat until conversion. Now, what is conversion? We will define later. We'll define this later. Huh? Wn plus 1. Okay, sorry. W. You're right. You're right. Yeah, thanks. I was teaching course with one of my director at Google. to Google engineers, right? And he used to make intentional mistake like this. And he used to say, huh, someone is awake. So it I mean, I remember him when you said this, I was tempted to say someone is awake. Anyways, thanks for this. Yeah, W0 to W. Good. So there are M+1 parameters. Good. Yes. Yes. You're all welcome to do it if you have a procedure. Yeah, people do it. This is I'm giving you a very, I would say, general procedure. You can do optimization. Of course, people try to come up with intelligent initialization, and it obviously helps you to get faster. Okay, but this is poor man's procedure. We still do not have any idea. Okay, but good. You thought something which is totally valid. Now, what is the first step? First step is to calculate the loss. I'll write in letters also, calculate BC loss. And you calculate this loss across all examples. Remember, you calculate this loss across all examples. So you iterate over entire training set. You iterate over entire training set. If you have millions of examples, you will have to do this iteration. Or you calculate in the vector matrix multiplication format. Calculate BC loss. It's the first step. Now, what do? You have the loss. What do you want to do now? You want to calculate gradient of the loss. Remember this slide in the morning? How were we doing it? Remember this slide. Correct. So we were here. Now we have this loss. We calculate the gradient and we move in the negative direction of gradient. All right. So let's calculate this loss. Now calculate the gradient of loss. So this is partial derivative notation. So you need to do this with respect to every W. Okay, I'm not going to write this equation. We'll figure out what that equation is. Okay, it will take us some effort to get here, but let's write the procedure first. Huh? We are going to calculate all these partial derivatives. This is, by the way, this is partial derivative, which is just like derivative with respect to a single variable. If there are M+1 variables, you're using one variable. All right. Next step. Step C. Now, next part is update, not update really. Set new values to parameters. How do you do that? So W0, remember this is not equal to, this is a set operator. W0, I say this is W0 new. W0 new is equal to W0 old minus learning rate times the partial derivative. Don't get scared looking at this equation. This is partial derivative. This is learning rate. Let me write this. Partial derivative with respect to W0. This is learning rate. And this is old value of W0. So you randomly initialized, you calculate loss, you calculate partial derivative, and go ahead like this. Keep doing this for each one of them. So I'll write this generally for jth weight or jth parameter clear? We still have not figured out how to calculate partial derivative. Don't worry about it. We'll figure it out. Huh? And finally, this important step, update W0, W1, all the way up to WM. The keyword is simultaneously. You update all of them once, right? At once. That's the procedure. That's the gradient descent procedure. What's the time? 3:47. Still have 10 minutes. We'll do this derivation in the next class, okay? But right now we'll just understand this well. Clear? That's it. Keep repeating this until conversion. And when the conversion happens, when these W values, W vector stops changing, or there is a very small change in the W vector, then you stop. Got it? Or there is no change for some time, you have hit a plateau, stop. It's very simple. This will be one equation which is vector matrix multiplication that will come here. And by the way, Zil is going to talk about, we don't have to do this in modern packages. In modern packages, we have a method to calculate partial derivative. You just need to supply the loss function, you get derivative automatically. That is great, but we should not forget this art. We should still know it so that we can verify whether the tool is doing correct, tool is not cheating us. Okay, so never forget this art. Though we use tool in practice, because in practice in standard software development, it's important to use components that are proven to work correctly. Got it? Simple procedure. Now, where are the bottlenecks? If you have millions of data points, where are the bottlenecks? See, what is happening is we need to calculate BCE loss. In order to calculate this BCE loss, we are going to do, we are going to sum up overall in examples. Correct? So you will have BCE of ith example, I running from 1 to n. If this n is, let's say, 1 million data points, you have to do this calculation over a large number of points. So one update of your algorithm, one single update, we'll have to do this calculation over millions of points. And remember, this gradient descent procedure we run for several iterations. So if you do hundreds of iterations, remember the amount of computation that will happen. Correct? And every update will be very slow because you are doing a lot of computation in the single loop, in this loop. Getting it? This is where the bottleneck is. Now, how do you fix it? Any ideas? I want you to discover some new algorithm. How can we fix it? Can we do something, some magic? Learning rate, see, learning rate is not a problem here. See, learning rate is not a problem. The problem is this particular 1 million additions. Somehow we have to reduce this particular part. Nothing will help because this will be like a lot of computation. I have given you a hint. Now, can you work on this? Yes, someone had some other, yes. No, you can do matrix, but you will have to do, I mean, 1 million points you have to process anyways, right? Matrix multiplication, yes, in one shot it will happen, but the processing, you need to process 1 million points already. I mean, always. Yes. Anyone else? No. Can we do this update on small number of examples? And why will it work? You remember this assumption we made in the morning? What was that assumption? What is the assumption of the training set on the training set? Data is independent and identically distributed. Correct? So we want to exploit that. And what we will do is we'll just make a small change in this step. Okay. And we'll get a new algorithm. A variation of this, really. It's called, I'll stop at 55. I'll give 5 minutes for questions and we'll continue in the next lecture. So we get a new algorithm called mini batch gradient descent. Mini batch GD. In mini batch GD, step 1 is as it is, step 2 is as it is, 2A, right? Here, what we do is inside 2, now we will run a loop. So we'll first make batches. Okay, let's make batches. So here, sometimes we randomly shuffle data, but let's not worry about that. So first is for each batch. For each batch. I'm writing in English without any symbols now. Okay, for each batch, what? Calculate DC loss to be, calculate partial derivatives, and to see as it is from GD, and 2D is also from GD. In fact, all these steps are from GD, but we do that only for batches. This is the only change. So you make small batches, but remember these batches are generally the size of the batch is close to some power of 2. We do that to get optimal disk read speed. So batch size is 64, 128, 1024, right? Some power of 2. Getting it? So now see, now this will happen, this will go very fast. Now this calculation is done only on handful of points. So you'll get update and you will get more updates. Correct? So now one such iteration of this loop is called as, this is an iteration, right? This is an iteration. This is a training iteration. Right? And one such complete iteration over the training loop over the entire data set is called as epoch. What is epoch? Epoch has multiple batches. Multiple batches covering the entire data set. Once you iterate to the entire data set, that is one epoch. And one epoch will have how many batches? So I'll quickly do this calculation. Number of batches in epoch is equal to number of training examples divided by number of, divided by batch size. Clear? Simple. This is called mini batch GD. Okay, there is one more variation which is called HGD, or stochastic gradient descent. In stochastic gradient descent, here, instead of a batch, we take exactly one example at a time. We just take one example and we can do this calculation. Right? But obviously, because we are taking single example, the gradient is sometimes erratic. Right? You might see, so in the morning, right? See, in the morning, we were looking at learning curve, correct? Learning curve was very smooth, like this. And that time we were running GD. With HGD, you might see something like this. So overall trend is that it is going down, but locally there are many variations. So sometimes in order to smooth this, people apply different techniques by averaging over last few gradients or whatever, or using mini batch gradient descent or something like that. So GD is also a bit expensive. So people mostly use mini batch gradient descent in order to get better efficiency of data processing. Okay, clear? Gradient descent, mini batch gradient descent, stochastic gradient descent. By the way, you can implement all these things in pure Python. Pure Python, just within 10 lines of code. 10 lines of code. Huh? Yeah, we should. Let's see. There will be a tutorial for that. Okay. You should do this, by the way. Each of these things, right? BC loss is one line of code. Partial derivative zero will show one line of code. Model, one line of code. So 3 lines of code and probably 15 lines of code for training loop. Within 20 lines of code, this algorithm will be implemented. If you implement algorithm, your fear of machine learning will go away. Trust me. Right? So you see lot of mass, but when you implement, right, you will see how this is getting converted into program. And that's where the beauty is. You will learn quite a lot. Okay, I think I should stop. I'm standing between you and your tea. Any questions? We have one more session at 4:30, but meanwhile, do you have any questions? Yes. Randomly meaning? Yeah. Correct. So do you mean to say, I mean, what I understood by randomly is before every batch you want to do shuffling? Yeah, generally that is what people do. Before every batch they do shuffling and then the batch is selected. That's how things are done. I have not written it just to keep it simple. Yeah. Yeah. So shuffle the batch, shuffle the examples and then create fresh batch for next epoch, so that you don't get identical batches epoch after epoch. So one epoch, before the first epoch, you shuffle the data, create batches, finish the loop. You come set to second epoch, shuffle the data, create batches, finish the loop. Keep doing this. Yes. Yes. Huh? HGD is even faster gradient descent. You get updates very quickly. Just by processing one example, you get update. See, these techniques are very useful when you're training model with millions and billions of data points. I mean, one update of full batch GD might take a day or two. Who will wait that long? So you can get quick updates and see whether model is making any progress. Otherwise, finish the process, do something else. Any other questions? Online? No questions. Hope people online are awake. Okay, anyway, this is tea time. So we'll meet at sharp 4:30. We'll start sharp at 4:30. Okay. We have a lot to cover. We have not yet covered this derivative, the derivation of partial, this particular thing, right? So I'll let Zeel first do the grad stuff, which is very easy. And then if not today, tomorrow morning, I'll complete this derivation. It will take about 15-20 minutes. But first learn the simple way so that you are more comfortable. Then we'll do harder way. In the maths, I mean, it's not really hard. It's just math that comes there. And that maths will need your concept of derivatives. You'll be taking some derivatives and things like that. Nothing complex. This is not complex if you understand it properly. Okay, all right. Thank you very much. One more session to go. We will have more practical now. Last session will be practical, so you will have a lot to do. You don't have to listen to boring lectures. All right. Huh? Yeah, you should get your laptops for the last session. All right. Thanks. We have some fun session planned. Couple of practical hands-on exercises.